Welcome back to Talk Tensors, the show where we talk tensors. Today, we're diving deep into two-stage segmentation of cervical tumors using PocketNet.
Quite a mouthful.
It is. But the work here is really pushing the boundaries of what's possible with AI in healthcare.
Absolutely, yeah. This paper is tackling, a really significant challenge in oncology, which is accurately identifying tumors on medical scans. And they've done it with an AI model that's not only, remarkably accurate, but also incredibly efficient.
So before we get into the nitty-gritty, can you give us that high-level overview? What's the core idea behind this PocketNet model?
Yeah, so the researchers developed this streamlined deep learning architecture specifically for medical image segmentation. And in this case, they trained the model to identify 4 key areas. On T2-weighted MRI scans of patients with cervical cancer, the cervix, uterus, vagina, and the tumor itself.
Okay, so why is focusing on T2-weighted MRI significant?
Oh, that's an important detail. So they chose T2-weighted MRI because it excels at visualizing soft tissues, which is crucial for identifying cervical tumors. And this is where their approach gets really interesting. They used a 2-stage method. So first, PocketNet identifies the organs, and then it focuses on pinpointing the tumor within that specific anatomical context.
That's clever. It's like a detective narrowing down the search area before zeroing in on the suspect.
Exactly, yeah.
But how effective is this 2-stage approach compared to other methods?
The results are really impressive. They achieved an average dissimilarity coefficient, or DSC, of 81% for the organs and 71% for the tumors.
I have to admit, I'm not as familiar with DSC. Can you break that down for us?
Sure. The DSC is essentially a measure of how well the AI's prediction overlaps with the actual tumor boundaries.
Right.
So a DSC of 71% means the AI is correctly identifying over 70% of the tumor's area. And that level of accuracy has significant implications for treatment planning.
That makes sense. So a higher DSC means a more precise outline of the tumor, which is critical for things like radiation therapy, where you want to target the tumor very specifically and avoid damaging the surrounding healthy tissue.
Exactly, yeah. And to further validate their model, the researchers tested it on a completely separate data set from the Cancer Imaging Archive, and the results, still incredibly accurate. And this consistency is a strong indicator that PocketNet is robust and has the potential to be used in real-world clinical settings.
Okay, so we've established that this 2-stage approach is accurate and consistent. But what makes it so efficient? You mentioned that earlier.
Yeah. Well, PocketNet is designed to be lightweight, requiring less computational power than many other deep learning models, and this efficiency is a game changer. It means that PocketNet could be deployed in hospitals and clinics that may not have access to the most powerful computing infrastructure.
That's a huge point when you think about global healthcare accessibility. So to put this all into context, let's talk about the evolution of deep learning in medical imaging. How did we get to a point where AI can identify tumors with such precision?
So deep learning is a subfield of machine learning that's loosely inspired by the human brain's neural networks. It's essentially a powerful pattern recognition engine. But the key here is the type of deep learning architecture used in PocketNet. They utilized convolutional neural networks, or CNNs, which are specifically designed for analyzing visual data like images.
So CNNs are kind of like the eyes of this AI model, allowing it to see and interpret the medical scans. But CNNs have been around for a while, haven't they? What makes PocketNet's application of CNNs unique?
That's a great question. It's not just about using CNNs, but how they're used. The researchers optimized the architecture to be streamlined and efficient while maintaining accuracy. They focused on reducing the number of parameters in the model, making it lighter, without sacrificing its ability to detect tumors effectively.
So it's like they've created a lean, mean tumor-detecting machine.
Precisely. And that focus on efficiency opens up a whole new world of possibilities, especially for resource-constrained healthcare settings.
This is all incredibly promising. But before we jump into those possibilities, I want to make sure we fully grasp the technical brilliance behind this 2-stage segmentation approach. Can we delve a bit deeper into that?
Of course, yeah. The 2-stage approach is really at the heart of what makes PocketNet so effective. Remember, the first stage focuses on identifying the organs, the cervix, uterus, and vagina, and this step is crucial because it provides anatomical context for the second stage.
So instead of just searching the entire image for a tumor, the AI is first saying, okay, here's the cervix, now let's zoom in and look for the tumor within the cervix.
Precisely. By first segmenting the organs, they essentially create a smaller, more focused region of interest for the second stage, which is all about tumor identification. And this targeted approach not only improves accuracy, but it also reduces the computational burden.
It's like giving the AI a roadmap of the body, saying, don't waste time looking for tumors in the lungs, focus on the areas where they're most likely to be found.
That's a great analogy. And this approach has another advantage. By separating organ segmentation from tumor segmentation, the model can be trained more effectively. Think of it like specializing in different tasks. One part of the model becomes an expert at identifying organs, while the other part becomes an expert at finding tumors within those organs.
I'm starting to see why this paper is making waves in the field. It's not just about achieving high accuracy. It's about doing it efficiently and with a clever approach that leverages anatomical knowledge.
Right, and this research builds upon a growing body of work that explores the use of multi-stage approaches in medical image analysis. And it's becoming increasingly clear that breaking down complex tasks into smaller, more manageable steps can lead to significant improvements in both accuracy and efficiency.
So this paper is not just a one-off success story. It's part of a larger trend in the field, pushing the boundaries of what's possible with AI in healthcare.
Exactly. And as this field continues to evolve, I think we'll see even more sophisticated approaches that combine deep learning with other techniques, like graph convolutional networks to model relationships between different anatomical structures.
Okay, this is all incredibly fascinating from a technical perspective, but let's shift gears a bit and talk about the bigger picture. What are the real-world implications of this research? How could PocketNet actually change the lives of patients?
That's the most exciting part. Imagine a world where this technology is seamlessly integrated into the clinical workflow. A patient comes in for an MRI, and within minutes, the AI has identified the tumor with incredible accuracy. And this speed and precision could have a profound impact on treatment planning and ultimately patient outcomes.
It's not just about identifying the tumor, it's about getting that information to the doctors quickly so they can make informed decisions about the best course of treatment.
Exactly. Faster diagnoses mean quicker treatment, which can be crucial in cancer care. And because PocketNet is so efficient, it could potentially be deployed in a wider range of healthcare settings, including those with limited resources. And this could have a huge impact on global health equity, ensuring that more people have access to advanced diagnostic tools.
This is what gets me excited about AI in healthcare. It's not just about pushing the boundaries of technology. It's about using that technology to make a real difference in people's lives.
Yeah, I completely agree. And it's important to note that we're still in the early stages of this technological revolution. As AI models like PocketNet continue to improve and become more widely adopted, we can expect to see even more transformative changes in how we diagnose and treat diseases.
Okay, so we've explored the technical details of PocketNet, its place within the larger landscape of medical image analysis, and its potential impact on patient care. But before we wrap up, I can't resist indulging in our favorite segment, Novel Notions.
Yes, the part where we let our imaginations run wild and brainstorm new research ideas inspired by the paper. I always enjoy this part.
Me too. So what mind-boggling idea has this research sparked for you?
Well, this paper got me thinking about the limitations of static medical images.
Limitations. Can you elaborate on that?
Yeah, so most AI models right now in medical imaging, including PocketNet, they analyze single snapshots of the body, like a frozen moment in time.
So we're looking at a single MRI or CT scan, which captures the anatomy at that specific moment.
Exactly, but the human body is dynamic. It's constantly changing, and tumors especially are not static entities. They grow, they change shape, they might even respond to treatment in ways that aren't always apparent from a single image.
That makes sense. It's like trying to understand the plot of a movie by looking at just one frame. You get a glimpse, but you're missing the context and the flow of events.
A perfect analogy. So my novel notion is this: what if we could develop AI models that analyze a sequence of medical images taken over time rather than just a single snapshot?
Okay. I'm intrigued. So instead of looking at one MRI, we'd be looking at a series of MRIs taken over days, weeks, or even months.
Exactly. We'd be capturing the temporal dynamics of the tumor, how it evolves over time. This would give us a much richer understanding of its behavior and how it responds to treatment.
It's like watching a time-lapse video of the tumor, seeing how it grows, shrinks or changes shape in response to therapy.
Exactly. And imagine what we could do with that kind of data. We could develop AI models that predict how the tumor is likely to behave in the future, allowing for more personalized and proactive treatment strategies.
That's incredible. We could anticipate potential problems before they arise and adjust the treatment plan accordingly, staying one step ahead of the disease.
Precisely. And this approach aligns perfectly with the principles of precision medicine tailoring treatment to each individual patient based on their unique tumor dynamics.
This is truly groundbreaking stuff. But I have to ask, what are the challenges in developing such an AI model? Where do we even begin?
Data is the biggest hurdle we need. Longitudinal imaging data, a series of scans for each patient taken at regular intervals over time. And that's no easy feat. It requires careful planning coordination and patient consent.
Right, because we're not just talking about collecting one scan, we're talking about multiple scans over an extended period, which can be logistically complex and costly.
Exactly. But I believe the potential benefits outweigh the challenges. Imagine the insights we could gain from analyzing these temporal patterns. We could identify early warning signs of tumor progression, predict responses to different treatments, and ultimately make more informed decisions that improve patient outcomes.
This has been an incredible deep dive. We've explored the groundbreaking research behind PocketNet, discussed its implications for the future of oncology, and even ventured into the exciting realm of time-aware AI models.
It has been a truly stimulating conversation, and while the challenges ahead are significant, the potential rewards are immense.
So to wrap things up, what's the one key takeaway you want our listeners to remember from this episode?
AI is rapidly transforming the landscape of healthcare, and the research we discussed today is a testament to that. PocketNet's innovative approach to tumor segmentation is pushing the boundaries of what's possible, and the idea of incorporating temporal dynamics into AI models opens up a whole new frontier of possibilities. It's an exciting time to be in this field, and I can't wait to see what breakthroughs emerge in the years to come.
Well said. Thanks for joining us on this deep dive, and to our listeners, thank you for tuning in to Talk Tensors. We'll be back next week with another groundbreaking paper, so stay curious and keep exploring the incredible world of machine learning.